Hello, grade 10. So we are going to continue the explanation about the chapter 3, okay, for physics. So for this presentation, we are going to explain about energy. So what's energy? What do you know about energy? What comes to your mind? Yes, electricity, light. So energy, the definition is the ability to do work or effect change. So any ability to do a specific work or to effect or to do any change in a body, it's called energy. Okay, so energy is much more broad than what we think. So energy can be in many forms. It can come from wide variety of sources. Okay, I'm gonna give you a few examples. And the unit of measurement is joules. This joules is 1 Newton times 1 meter. So it's the ability to do work. Which work? For example, to do a movement, for example, 1 meter, or to do a change. And the energy that I use to do this change. So when I multiply the Newton by meter, I have the joule. Okay, that's the unit of energy. So 1 joule is 1 Newton times meter, 1 meter. So the energy can have different sources. For example, elastic energy. Elastic energy is the energy that comes from the compression or extension of an object. For example, when we stretch elastic, there is some energy here that is like stored. So when we stretch, we liberate this energy that makes this guy to move. Or the compressed spring. So when we compress, there is a energy stored here in this spring. So this is also called elastic energy. Electrical energy, that's what it usually comes to our mind when we talk about energy. So it's the energy from the movement of electrons from one atom to another. So remember where the electron is? So electrons is inside an atom. Where in the atom, like specifically? Yes, in the electrosphere, not in the nucleus. So when the electrons are moving from one atom to another, we create electrical energy. For example, when we have a power plant, so this power plant can be, for example, hydraulic plant or nuclear plant, doesn't matter which plant we have. But this plant takes the energy from the source that we use and transforms it into electrical energy. Or there is another one, battery. Why battery we produce energy? Because inside the battery here, we have chemical reactions happening that creates this energy. And this energy is transformed to electrical energy from your tool, whatever you are using this battery. Or you can create energy by a generator. So there is some portable generators that you can put some fuel here. Then this fuel, by the movement of the generator, is going to create an electrical energy. Another source of energy is thermal. Thermal comes from the word thermal. So thermal means related to temperature. Temperature is related to motion. So motion of all particles. So when you move a particle, we create a thermal energy. For example, the fire. So when we move the fire, when we have fire, we are liberating this thermal. That's why it's hot. So because it's liberates this energy. Or for example, a heating element. So usually we have this in our homes, in our stove. So when we plug it in the electrical energy, this electrical energy is transformed to a heat, to heat. So transformed into thermal energy. Or the sun. The sun creates a lot of thermal energy. That's why the sun is hot. Another energy is the radiation. Radiation is the energy contained and transported by electromagnetic waves. So what does that mean? It's like small particles that moves, creating electromagnetic waves. Okay, so for example, this happens in light bulb or radiographic equipment, our microwave, radio, television, our cell phone, the sun again. So the sun has thermal energy but also radiation energy. So the UV lights, for example, are example of radiation energy. And the fire again, because the fire liberates thermal energy but also radiation energy. Chemical energy. Chemical energy are the energy stored in molecular bonds. So our body has a lot of chemical energy, so it's stored in our bonds. For example, apple or any food or our bodies, we all have chemical energy. Candle wax, so the wax that makes this has chemical energy stored inside their molecules, so makes this to keep the fire on. Or fossil fuels. So do you know what's this? Petroleum. And what is petroleum comes from? Yes, from dead animals or plants that lived millions and millions of years ago. So this fuel here, why it's chemical? Because it comes from bodies. So it comes from dead bodies. So basically comes from other organisms. So every organism has chemical energy stored in our molecular bonds. So because this is formed by dead bodies of dinosaurs, plants, animals that has lived millions years ago. So we have a lot of chemical energy stored here. Another one, wind. So wind is the movement of air. So this movement of air creates this energy that we can use this energy in power plants that use this wind. So the movement of these helix creates electric energy, is transformed into electrical energy. Sound energy. So sound energy is the energy contained that is seen and transported by sound waves. So, for example, the sound that we are listening right now, it's a type of energy. Or the music, if you are listening to music, is another sound energy. Hydraulic system or hydraulic energy is the flow of water. So hydraulic energy is the energy stored in the water. That's why waterfalls are so powerful. We can make an electrical energy from it because when it goes down, a lot of energy is stored here that can be transformed into electrical energy. Or a river also has, but it's stored, but there is a lot of energy here, but we can just use it when it's in fall. Then we can use this to move a turbine. Nuclear energy. So nuclear energy is the energy inside an atomic nuclei. So before we had the electrical energy. Electrical energy is the energy from the electrons. So the electrons are in the electrosphere here. These are the electrons. So the electrons creates electrical energy. But nuclear energy is the nucleus, is the energy that is here inside the nucleus. Okay, so this is the nucleus of the atom. This energy is much more powerful than the electrical energy. So there is much more energy here. To put the protons and the nucleus together, we need a lot of energy. So when you break this, a lot of energy is liberated. And this also happens in sun because all the chemical reaction that's happening here, it's basically the nuclear reaction. That's why it liberates so much energy. And that's why it liberates radiation as well, and thermal and everything. Okay, so these are the main kinds of energy. Now I'm going to talk about the law of conservation of energy. You already know what's the law of conservation of energy states. So nothing can be created or destroyed. It can only be transformed or transferred. Yeah. So the amount of energy can only be transferred or transformed. The amount of energy in an isolated system also always remains constant. So the energy that we have in a system is always constant, cannot be loosed or created, only transferred or transformed. So what's energy transfer? Transfer is the movement of energy from one place to another. So when we basically transfer from one place to another. And what's transformation? So transformation when we change the form of energy. Okay, so when we change, for example, from electrical to thermal or thermal to radiation. So when we change. Here is an example of a power plant. So a power plant, for example, creates electricity. This electricity is transformed. So transformer. So it's transformed and transmitted to long distance until our house. So in our house, we can use this electricity and transform into thermal, for example, to heat the water. So we transform this electricity to the thermal. Or transfer. So the energy here is transferred to the wires until our house. So, for example, let's say this is a power plant that uses fossil fuels, for example, petroleum or coal. So we are transformed from chemical to electrical. So we are using fossil fuels to make electrical energy. This is transfer or transformation? Yes, transformation. And from the power plant to our house, what we are doing? We are transforming the energy or just transferring the energy? Yes, we are transferring. So from our home, from the power plant to our home, we are transferring. But what's happening here? A transformation. And inside our house can have transformation as well, as I said. If you use this electricity to heat the water, you are transforming the electricity to heat, to thermal energy. Now, it's not always 100% efficient when we transform energy or transfer. So energy efficiency is how much is the percentage of energy consumed by a machine or system that was transformed into useful energy. So how do you calculate? So a machine or system can only convert parts, not everything of the energy. The other part is transformed into another form or dispersed. Okay, so it's very difficult to use 100%. For example, for the car, if you use, for example, 5 gallons of gasoline, only 12% of this is gonna be used to run the car. Okay, so the other 88% will be lost or be dispersed to the car, to another part of the car. It's gonna create thermal energy and everything else. So only 12% will actually be used to run the car. So it's not so efficient. Light bulb. The incandescent bulb only can convert 5% to produce light. So only 5% of this is used to produce light. The other are, for example, transformed into thermal. So if you touch here, you're gonna observe that some heat. So the bulb is gonna be heat. So it produces also thermal. We don't want to, but we also produce, okay? So only 5% is used to produce light. The other 95 is dispersed or transformed in something else. So how do we calculate? So it's a formula, okay? So we take the useful energy and the amount consumed or produced, okay? It depends on the problem. Then we divide both of them and multiply by 100. Here's an example. So a certain light bulb consumes 200 joules of electrical energy per second, but only emits 25 joules of light per second. Calculate the efficiency of this bulb. So the first thing you need to do when you have a problem, highlight the most important information. So it consumes 200 joules, but just produce just the useful, so just emit 25 joules. So let's make a list. So the useful energy, the energy that we actually use it, is 25 joules. And the consumed energy is 200 joules. So how do we calculate? So 25 divided by 200, so amount of useful, 25, amount of energy consumed, 200. After you divide, you multiply by 100, so you have the percentage of the energy efficient. So in this case, we have 12.5% of energy efficient for this light bulb. Another example. A certain large wind turbine is able to transform 1,500, so 1,500,000 joules of mechanical energy into 1 million joules of electrical energy per second. How much thermal energy does this turbine waste? So, how much we waste? So, and calculate the efficiency of this turbine. So the useful energy is 1 million joule per second. So it converts from the 1,500,000, it converts only 1 million. And the produced energy is 1,500,000. So how much do we waste? So we waste, in this case, 500 waste. It's not so much at all. How do we calculate? So the useful energy divided by the produced energy and times 100. So the energy efficiency in this case is 67%. Okay. Now, what's thermal energy? We're gonna explore a little bit more. So thermal energy is the energy contained in a substance that is divided by the number. And the heat. The heat is the transfer of thermal energy between two environments with different temperatures. Heat always passes from the warmer to the cooler environment. For example, ice and water. When you put ice inside a glass of water, what's going to happen? Water will give off heat and ice absorbs that heat. So what happens to the water temperature? Yes, it's going to decrease. So the water temperature is going to decrease. Why? It's give off the heat. So that's why the water temperature decrease. And what's going to happen to the ice? It's going to melt. So it's going to absorb this energy and it's going to melt. So it's going to turn from solid to liquid. So what's the relation between heat and thermal energy? There is a relation that we use with the Q. The Q measures in heat, in joules, and E, delta E, delta is variation, okay? So this symbol here means variation, is the variation in thermal energy. So how much the energy has changed from one situation to another. How do you distinguish now heat and temperature? Temperature is the measurement of the degree of agitation of the particles. So just relate to how much the particles are excited. It's like there is agitation. And heat doesn't depend only to the speed of the particles, their growth of agitation, but also their mass and the type of particles. Okay, so depends on the speed, mass, and type of particles. For example, if you have a glass of water or a stream or a river with the same temperature. Let's say the temperature of a small cup of water might be the same as the temperature of a river, okay? But the temperature are the same. But what about the heat? The heat is the same? The heat that is stored is the same? No. Why? The river has more heat because it has more volume of water. So if you have more mass, more thermal energy. So in this case, if someone asks you, what's the temperature? Are they the same? Yes, the temperature are the same. The temperature are the same. But the thermal energy is not. Why? Because the energy stored in this river is much more. Why? Because the river has more volume, has more mass of water. So heat doesn't depend just on the agitation of the particles, but also to the mass and the type of particles. So if you compare two different substances, it's going to have different thermal energy as well. So let's make an example. Let's say a cup of water and a large pot of water both have the temperature of 50 degrees Celsius. Okay, so a cup of water and a large pot of water has 50 degrees Celsius. Which one has more heat energy? The cup of water or the large pot? The pot of water. Why? Because it has more mass. What about which one is hotter? Which one has higher temperature? Yes, none of them. Why? Both have the same temperature. No, so none of them is hotter than the other because the temperature are the same. What's changed? The heat energy. The heat energy inside is higher in large pot because it has more mass. Another one. Can a large iceberg have more heat energy than a cup of boiling water? What do you think? A large iceberg, so ice, can have more heat energy than a cup of boiling water? Yes. Why? Because it has a large mass. So when you compare the volume of a large iceberg, it has much more mass than the boiling water. Here we are talking about the same substance, okay? So both of them are water. That's why I can make this comparison. So a large iceberg has more heat energy. So if you prefer to be hit by a large iceberg or a boiling water, prefer a boiling water. It's gonna have less damage in you than the large iceberg because the energy stored in the iceberg is much more than in the boiling water. Okay, so it's not due the heat. The temperature has just one component, but it's not the main component of the heat energy that has inside the substance. Okay guys, so thank you so much. So here there is some exercise from your book. I'm gonna scan it and put in the Google Classroom. Okay, so you have access if you don't have your book. So you can do it and send me back. Okay, if you have any question, please send me an email. Okay, thank you.